satisfação ter uma plateia grande assim, para refletir, né, sobre esse desafio que a gente tem pela frente, né? Quer dizer, será que existe uma quarta revolução industrial na nossa frente, né? Tem uma grande transformação acontecendo, né? Afinal, essa plateia aqui, né, nós somos herdeiros, né, metalurgistas, herdeiros da criação da primeira revolução industrial, né? Fomos nós que criamos isso. Esse pessoal, os engenheiros mecânicos dizem que eles inventaram a máquina a vapor e isso foi o começo da revolução. Mas se não tivesse gusa para fazer aqueles cilindros lá, não ia ter máquina a vapor nenhuma, tá certo? Então, nós somos assim, não queremos aparecer muito, então a gente deixa o James Watt fazer isso, né? Mas, quem sabe, o nome dos metalurgistas da época, o John Wilkinson e os outros daquela turma lá de Birmingham, merecessem mais destaque. Então, 200 e tantos anos se passaram, né? 250 anos se passaram, e nós estamos aqui frente à quarta revolução. E hoje, em particular, a gente vai querer abordar essa questão, né, no título da nossa sessão. Está aqui, Indústria 4.0, Big Data Analytics para otimização dos processos. E essa sessão, então, temos que agradecer todo o apoio da ABM, toda a comissão organizadora do Congresso que nos deu um grande apoio. Quero agradecer também ao Walter Saito, da Prime Metals, que junto comigo, e muito mais do que eu, para falar a verdade, participou da organização, de juntar essas pessoas, de discutir a temática e de planejar o que nós vamos conversar aqui, né? Então, agradeço muito. Cadê o Walter? Walter está ali. Obrigado, Walter. Fundamental a presença dele. E antes de apresentar os 4 palestrantes nossos aqui, eu gostaria de comentar, então, o que eu e o Walter discutimos várias vezes, né? E um pouco da ideia que veio surgindo, de que temática a gente quer discutir, e é uma certa provocação, né? Então, imagina que o alto forno tivesse um presidente, tá certo? E a gente, então, estamos em eleição, só se fala nisso. Então, quem são os 4 presidenciáveis? Eu imaginei, isso foi uma ideia, né? Bem mais complexa a história, deve ter mais candidatos. Mas vamos pensar em 4 candidatos, né? De um lado, nós temos o pessoal que opera o alto forno mesmo, né? Os engenheiros que estão lá no dia a dia, acompanhando tudo o que está acontecendo no alto forno, conhecem o alto forno intimamente, conhecem o resfolegar do alto forno, o cheiro do alto forno, conhecem tudo. É uma turma que... Aquela frase famosa, que tem muita sabedoria dentro dela, né, de que na prática a teoria é outra, tá certo? É um pouco o que tem ali, né? O conhecimento todo que está acumulado. Por outro lado, tem a turma, vários nomes possíveis, vamos chamar de metalurgia, né? A turma que, né, nasce com a segunda revolução industrial, né, com a termodinâmica, tá certo? A termodinâmica é um produto da segunda revolução industrial, né? E essa turma, então, vem avançando rapidamente, entrou com tudo na terceira revolução, está modelando, né, mecanisticamente os processos metalúrgicos que estão lá. Então, essa turma está super forte e tem muita opinião a respeito de como conduzir o alto forno, certo? O terceiro presidenciável, né, é a turma da automação, né, porque, afinal, eles vêm cada vez conhecendo mais a operação desse alto forno, medindo coisas e estabelecendo cada vez mais loops de controle e etc. Na verdade, quem controla o alto forno somos nós, a turma da automação, certo? Então, o partido, né, da automação é um partido forte nessa eleição. E o quarto candidato certo? O quarto presidenciável é essa turma nova que está chegando aí, o pessoal da TI, certo? O pessoal da tecnologia da informação. Né? Essa turma vem com toda essa vontade de usar o Big Data. Né? Essa turma que vai pegar e falar, vocês estão jogando fora dados. Né? Essa turma da automação mede, controla e depois joga fora. Não, eu quero manipular esses dados aí e deles eu quero tirar, estabelecer os algoritmos que de fato podem ser usados para controlar o alto-forno. Né? O ano passado, pelo menos entendi assim, na sessão de quarta revolução do ano passado, né, essa questão já apareceu e um pouco assim, exagerando, né, pensando no futuro, né, não vai mais precisar de engenheiro, certo? Quer dizer, cientistas de dados são capazes de fazer isso. Né? Então, agora, será que é assim? Será que vai ter que haver uma eleição e um desses quatro vai mandar? Ou será que é possível, né, juntar essa turma? Vai ser possível juntar isso? Né? Ou há conflitos mais profundos entre essas turmas? Eu ouço dizer que essa história, facetas dessa história que eu estou contando, está acontecendo em vários lugares por aí. Então, refletir sobre ela, né, e refletir sobre a nossa capacidade de lidar com esses quatro saberes tão diferentes, né, e como é que nós vamos juntá-los para otimizar a operação de seja lá o que for que a gente quiser, né? É esse grande desafio, né, que a gente está vivendo na quarta revolução industrial. Então, vai ser sobre isso que a gente vai falar. Né? Então, nós teremos aqui, falando, o Dr. Kurt Herzog, que é o chefe da indústria 4.0 da Primetals Áustria. Ele vai nos falar em inglês. O ano passado ele já apresentou aqui para a gente uma outra visão dessa história. O professor Guilherme Lenz, que é um professor da Escola Politécnica e que tem pensado sobre essa questão, já trabalhou na indústria, conhece isso, então está juntando um pouco um olhar acadêmico sobre essa eleição. O senhor Heiko Wolf, chefe do Future Lab da PSI Metals, Alemanha, é o terceiro palestrante, e o Marcelo Belens, que é assessor digital da Microsoft. Então, serão essas quatro pessoas que vão falar, e eu, então, chamo, em primeiro lugar, o Sr. Kurt Herzog, para assumir aqui o pódio e fazer a apresentação para nós.
It's great to be here. Second time in a row. Unfortunately, I did not use this 1 year span to learn Portuguese, so I have to do my speech in English. I'm talking about a system or an approach we call through process optimization, which is an integrated solution for steel production to achieve best quality, highest productivity, plus lowest cost, which seems to be impossible to a certain extent. And I'll try to use the picture that Professor Landgraf used of these 4 disciplines that are working against each other or together, being a candidate for the presidency. So through process optimization, what is it? It is a combined approach of an IT system we call through process quality control and know-how elements, through process know-how elements. And referring to the metallurgists in the 17th, 18th century who did a great job, many things have changed since then. But one thing has not changed, the material we are dealing with. It's still behaving in the same way. And if we are honest to ourselves, we still do not fully understand how it behaves. So collecting this know-how is essential, but know-how is worth nothing if you don't use it. So our approach is to combine know-how with the IT system to create this benefit. Where is this system placed in the digital landscape of a steel plant? You could say it is somewhere between the process automation, level 2 automation systems, and the production management systems, MES systems, the level 3. This is where it is placed, and it is collecting all relevant process and quality data along the entire production chain, and this is quite new. It is really considering all the process and not only individual production units. I just want to give you a quick functional overview, and we see the 4 candidates in this overview again. So we start with data. If we talk about data analytics, we have to start with data. So we collect data from all the production facilities in a very high resolution, verify that the data is correct, because if you do data analytics with wrong data, the result most likely is not correct. And then we do something that is very important to do further analytics. We project the data to the product length. So all the process data, all the quality data that is collected is clearly correlated to a certain spot on the intermediate or final product. So this means if there is a piece of cold rolled steel, we can exactly say what happened to that piece in the POF, in the ladle furnace, on the caster, in the hot strip mill. All the data is more or less correlated to this point. And this data is the starting point. So this is what the automation guys provide, the data. Now we come to the guys on the shop floor who have all the experience. There is a lot of human know-how available. Sometimes you could say it's digitized because there are work instructions in an Excel file or in Word. Sometimes it's not digitized because there are just notes in a notebook. And we digitize this know-how. And then we combine this. Now we bring the thermodynamics and other scientists into the picture. We use prediction models. So out of the data that is collected, we use prediction models to have a view into the future, and we directly use this data. And we combine this data now with the know-how that is in the know-how database, and carry out several functions like parameter evaluation, quality grading, root cause analysis if something goes wrong, compensational action, statistic process control, KPI calculations. So by doing that, we use the data we collect combined with the know-how to stabilize the production. We use the results of the evaluation to carry out process control, and for sure we have a huge suite of visualization and reporting tools to analyze the data as well. Now the data analysts come into the picture. The data we collect is an excellent basis to carry out data analytics and to generate new know-how and to generate new data-driven prediction models. So collecting data, combining it with existing know-how stabilizes the production, and analyzing the data is generating new know-how to further optimize the processes. So this is more or less an overview of what we do in this through process optimization system, and I will go into some details in the next slides. So as I already said, we collect data along the entire production process, and we can generate a genealogy. Many steel producers are collecting data in all the production units, but they are not in relation with each other. And if you want to analyze what is the influence of one process step to the next process step, this data needs to be correlated. So what we generate is a so-called product genealogy. So to have all the data combined on the finished product. So we track each slab, each individual intermediate product, if it is turned, if it is cut, track it, to do this data projection later on. And as I said, this is the result then is an excellent basis for data analytics. And I'll give you some examples on that later on. We have talked about the know-how database and what do we do with this know-how database. So it starts with conformance checks after each production unit. So after each production step, relevant parameters are checked if they are in range or if they are not in range. And if they are not in range, we act on this. And we have set up a rules engine in this system which gets the inputs and the data from the automation systems and limits maybe from the production management system and evaluates if all the parameters are in range. And if it's okay, then it's fine. And if it's not okay, then we do three different things. First of all, we support root cause analysis to find out what is the root cause for the problem, for the deviation. Second is we define corrective actions, what can be done that this does not happen again. And the third thing is we propose or execute compensational actions. So what can be done further downstream in the production process to bring the product back into the specified ranges. So there is one rather simple example. At the end of the blowing process, it is detected that the end blow target temperature was not reached and the temperature is too low. So now the system comes up in supporting to find the root cause analysis with a list of potential root causes and supports the operator in finding out the root cause. In that case, the root cause obviously was that there was new materials used in the process which have not been, where the parameters of this material have not been properly entered into the material database, so the process model, the blow-end calculation did not calculate properly. So this would be a corrective action to make sure that this problem does not occur again. And the compensational action in that case would be, for sure a reblow has to be carried out to reach the temperature, and the compensation action would be that the casting speed for the caster for which the ladle is scheduled is reduced to make sure that the casting sequence is not interrupted. So this would be a very simple example of a root cause analysis, corrective and compensational actions. The system also collects all the data from the surface inspection systems, and from one single terminal you can really have an entire overview of all the surface inspection data, and this is a very valuable support to analyze in product development and also in case of customer claims. Process data inspection, you can have a look at several process parameters from several production units for one final product, or you can have a look like shown here, 2 exit temperatures for 2 different coils on the same production facility, or you can even have lots of coils and draw something like density plots and signal envelopes for certain signals. And this is supporting to find problems for the quality engineers. Also for defects, and we can draw density maps. As I said, we find root causes and propose compensational actions, and this is an example for a screen. So there is one deficiency was detected, that the exit temperature on the finishing mill was not within range. So there is a proposed compensational action which is reduce the pickling speed and the PLTCM, and then there are several root causes. And here you see statistics how often the individual root causes were identified as being the root cause, and this again allows you to do statistics on the root causes and improve the process. And the system guides the operator and supports him with information. So on the investigation of the violation of the process parameters, the operator gets a lot of additional information, and also finding the root cause is supported with proposals how to identify root causes and how to correct them. And for sure, we have a big suite of KPI and reporting dashboards to have full transparency on the production process. Who are the users of this system? So the system is set up in a way that it can be used by a huge group of users, and all of them use things like reporting, KPIs, business intelligence, statistic process control. For the process engineers and the product development and the R&D people and data analysts, the data mining capabilities are extremely important, and I'll give you some examples on that later on. Technologists and process engineers use the quality and process assistants, and the shift engineers use the operator assistants. And for sure, for each of those user groups, the screens can be set up individually that they really fit to their demands. Now I'm coming to what we do with data analytics, and I use examples from a reference plant we have set up in China, where we have connected 2 production sites, which are approximately 70 kilometers away from each other, 16 production units, 6 surface inspection systems. We collect about 8,000 process parameters in high resolution. We track about 100 KPIs, and we have implemented more than 400 rules in this system. The daily amount of data is something like 50 gigabytes, and our customer is producing about something more than 300 coils per day. And what have we done there with data analytics? Our basic approach on data analytics is, first we need a clear definition of the problem. If you want to find the needle in the haystack, you have to know first that you want to find a needle, and second, what does a needle look like? Otherwise, you just find something. So we need a clear definition of the problem. We have to understand the data we are working with. Are there missing values, constant values, outliers? So we need to clean up the data. And then we can apply data analytics methods, machine learning methods, to find new insights. And these new insights then again are brought back to the knowledge database and used in the automation systems. And I give you 2 examples now what we've done. First one, we investigated where scale defects on the PLTCM are coming from. And interesting to see, analyzing 150 data points, 150 variables in our model, two of those variables had the highest importance. The first one was the rolling time on the hot strip mill, and the second was the caloric value of the gas used to heat the heating furnace on the hot strip mill. So what we've done, we've clustered the data sets we had into clusters, into bins. So the red ones are the good ones, the white ones are average, and the black ones are the bad ones with a lot of scale defects. And if you look at this plot, rolling time versus heating value of the furnace gas, you see that there is a lot of bad products up in that area. So if you isolate that and just have a look at that area, you see that in that area almost all the bad coils are, and there are almost no good ones. So this means that the defects occur if this customer uses high calorific gas in the reheating furnace, natural gas, and if the rolling time is short. Both findings are a little bit into contradiction of what we would think would be the truth. And now this is, again, what's very important when you do data analytics. You have to also analyze the result. And it is very likely that it's not the gas that makes the difference, but it is the setup of the burners. So this is not a general statement that natural gas is not good and blast furnace gas is good in the reheating furnace. Maybe the burners are just tuned in a way that other effects influence the scale. So this insight is only valid for this furnace in this setup. And the second thing is the rolling time. We would expect that a short rolling time causes less scale than a long rolling time, but it's the other way around. And the reason for that is long rolling time shows that the coil box is used. And this makes the difference. So again, the result has to be interpreted correctly. Second example, a customer wanted to develop a new product, dual phase steel, and he faced the challenge that the tensile strength was fluctuating a lot. So there is a scatter plot here showing that would have been the target area, and there were many coils where the result was out of that range. So what did we do? We pre-selected 200 critical process parameters, did our data analytics, and we found out parameters along the entire production chain that are heavily influencing the tensile strength. And after having set the parameters in the production systems to what we found, the situation dramatically improved. Summarizing, this through process optimization is a holistic approach to improve the overall performance, and it is a combination of an IT system with know-how, and this is important, I think. It supports a quick understanding of the complex technological problems, and it helps to quickly find answers, which saves resources. And it supports the data-driven approach to improve the technological and metallurgical understanding. It is the perfect tool for quick product development, and coming back to what Mr. Landgraf said, to the guys on the shop floor with all the experience. I think most of the steel producers are facing the fact that these experienced people retire, and there are not many that experienced left. And many of the steel producers are facing a decrease of know-how and experience in their staff. This system supports to digitize this know-how and keep the know-how in the company. And combined all that together, this system supports to get into a better cost position. Thank you very much.